Okay, so the next thing I want to do is go through question 2 from the relativity homework, which you handed in at the end of last term, which I'm just about to get back to you. I know it's been a bit of a long time, I do apologise for that. So here we have an antiproton with total energy 1.6 GeV. Approaching a proton at rest. And so its total energy is just its mass energy. And of course, the mass of the proton times c squared is 0.94 GeV, or roughly, it's 938 MeV, but I've used the same number of significant figures in the two cases. And so after this collision you get the emission of two photons, and you're told that one of the photons is emitted in the same direction as the direction of incidence of the antiproton originally, so we'll call this gamma 1, and so this guy has an energy E gamma 1, and then the other photon is emitted in the opposite direction, we'll call that one gamma 2, and it has energy E gamma 2. And the first part of the question is find E gamma 1 and E gamma 2. Okay, so the way you can do this is just with ordinary energy momentum conservation. So first we'll conserve energy. So we have, for final state energy, we have E gamma 1 plus E gamma 2, and that's all the energy we've got. And in the initial state we had the energy of the incident antiproton, P primed, plus the energy of the target, which is at rest, so that's just its mass energy. So that's my energy conservation equation. For momentum conservation, the two momenta are equal and opposite, so we'll use P gamma 1 to denote the magnitude of the energy of the momentum of the first gamma, and P gamma 2 to denote the magnitude of the momentum of the second gamma. And if they're magnitudes, then the signs of the direction of the momenta are expressed in signs. So we have that P gamma 1 minus P gamma 2, because its momentum is minus the magnitude P gamma 2, so that's that minus sign, is equal to the momentum of the incident antiproton. Now the incident antiproton has energy 1.6 GeV, so its momentum P of the antiproton is going to be, well, multiplied by c, is the square root of E P prime squared minus MP bar squared c to the fourth. That's from the energy momentum mass relation. And that's the expression for the magnitude of the momentum of the antiproton, and the target of course isn't moving, so it doesn't have any momentum. So on the right hand side of this equation we just have that square root, the square root of E P bar squared minus P bar squared c to the fourth. And of course we can not bother writing the bar on the mass, because the proton and the antiproton have the same mass. So we've got these two simultaneous equations. Sorry, there's c's here as well, because Cp is equal to the square root of that difference. Because these are photons in the final state, c times the momentum of a photon is just the energy of the photon. So just for massless particles, that is, that's certainly not true for particles that have mass, because the mass comes into play as well. But for photons we can rewrite, instead of Cp, we can write the energy of gamma 1 here. And similarly for the other photon. And crucially, the minus sign stays around. So we've got these two simultaneous equations. And the nicest way to solve these, I think, is just to add them vertically. So if you add the left-hand signs, you get 2E gamma 1, and the E gamma 2 contribution cancels. And on the right-hand side, you get something fairly complicated. EP bar plus MPC squared plus the square root of E P bar squared minus P squared c to the fourth. And so that means that the energy of gamma 1 is equal to 1/2 of this expression, EP bar plus MP C squared plus the square root of P bar squared minus MP squared C to the 4th. Let's not put in any numbers yet, let's just leave that expression up there. The question is, what is E gamma 2 going to be equal to? Well, we can just go back to the energy conservation equation and rearrange it. So if we just put this E gamma 1 on the right, we get that E gamma 2 is equal to EP bar plus MP C squared minus E gamma 1, which is, writing everything out, E P bar plus MP C squared minus 1/2 E P bar minus 1/2 MP C squared minus 1/2 the square root of E P bar squared minus MP squared C to the 4th. Okay, but this expression is actually very simple because the EP bar can have subtracted from it minus 1/2 EP bar just to give you 1/2 EP bar, and the MPC squared minus 1/2 MPC squared is again just 1/2 MPC squared, and then this minus half the square root remains. But notice it's basically the same expression as the expression for E gamma 1, but with the plus sign before the square root replaced by a minus sign here. So the expressions for E gamma 1 and E gamma 2 are quite similar. They differ only by a minus sign and the square root. So we can write E gamma 2 equals 1/2 E P bar plus MPC squared minus the square root of E P bar squared minus MP squared C to the 4th. So there's some algebraic expressions for the energies of the two photons. You can stick numbers in. When you stick numbers in, you discover that E gamma 1 is equal to, and here you use the energy up here, 1.6 JeV plus 0.94 JeV plus the square root of 1.6 squared minus 0.94 squared. And if you're careful, you get the answer, which is E gamma 1 is 1.9 JeV. Right, and then similarly for E gamma 2, the only difference is that minus sign, and so you get for that 0.62 JeV. And so that's the answer to the first bit. But let's hang on to these algebraic expressions for the energies, because they'll be useful in doing the next bit the hard way. There's two ways to do the next bit, so we're going to discuss both of them.